Chapter 6, Section 1. It is all about producing electricity from magnetism. Before starting, we need to remember some important notes from Chapter 5, Section 3. Whenever we have a charge that is moving perpendicularly in a magnetic field, it will experience a magnetic force which can be found by using right-hand rule. Now let us have a wire. A wire is a conductor because it contains free electrons. It doesn't contain extra electrons, it contains free electrons. So the electrons that we have inside the conductor are free to move. The positive charges are not free to move. Let us move this wire inside a magnetic field. When we move the wire, we are actually also moving the charge. So the charge will experience a magnetic force, which we can find the direction of the magnetic force acting on the charge. And since the only moving charges are electrons, the force acting on the electrons will be downward when you use the right-hand rule. After a while or a moment, you will see that the negative charge will accumulate at the lower side of the wire and the upper side have lost electrons, so it will be positively charged. As you see, this resembles a battery because in a battery you have one side as positive, one side as negative. Why this side is positive? Because it is filled with positive charge. Why the other side is negative? Because it is filled with negative charge. And having a separation of positive and negative charge is called as potential difference. Now, so in this wire, as you see, I have separation of charge. So I also have something like potential difference. I will not call it as potential difference because we have produced this one by force. So when we produce something by force, we called it as induced. So the separation of charge here is called as electromotive force. Simply EMF. The symbol will be epsilon. For this straight wire, the EMF can be found by the magnetic field. The stronger the magnetic field is, the more EMF will be. The greater the length of the wire is, the bigger EMF will be. The faster you move the wire, the greater EMF will be, and multiplied by sine theta, which comes from the equation of the magnetic force. Epsilon and V, they have the same job. Both of them have a unit of volt. If we write the units, it will be like this. Volt is equal to Tesla times meter per second, which will be equal to volt is equal to Tesla meter square divided by second. You actually have seen this in chapter 5 when it rearranges this equation to have Tesla alone. So Tesla will be equal to, let's write that one too. Tesla will be equal to volt times second divided by meter square. This is the production of electricity by using magnetic field. The production of electricity by using magnetic field is called as electromagnetic induction. The best way to have electromagnetic induction is the change in flux. Actually, this is the only way to, because whenever you change flux, everything will change. From chapter 5, flux was A, B, cosine, theta. So we have these three ways to change flux. Whenever we have change in flux, we have electromagnetic induction. And whenever we have change in flux, we have induced EMF. We have produced this one. Induced means produced. And whenever we have induced EMF, we have induced current. Whenever we have induced current, from chapter 5, again, we know that every current has its own magnetic field, which is called as induced magnetic field. Flux can be changed by three ways. The first one is change in area, which is area final minus area initial. The second way is by changing magnetic field. We have two ways to change magnetic field. A is simply by having a relative motion. How can we have a relative motion? Let's say that we have a coil. We also have a magnet here. We 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 this is a coil attached to a resistor, and this is a magnet. As I move the magnet with respect to the coil, it is having a relative motion. Now, this is a coil. I can also move the coil. Again, this is also a relative motion. If you move any of them with respect to the other one, you have relative motion. But now I am moving both of them together. I don't have any relative motion. I don't have any relative motion. Let's put it here. For part B, I can move a coil in and out of a magnetic field perpendicularly. So the direction of the velocity is always perpendicular in all of the three cases that I will be talking about in a moment. First one, second one, and third one. So in all three cases, I will have the plane of the coil with respect to the magnetic field. In the first one, the plane will be perpendicular. In the second one, the plane will be at an angle. And in the last one, the plane will be parallel. This is out of the field, and this is into the field. You can change their places. It is not very important. And we have a change in flux, and we have induced EMF. The most important thing in chapter 6 is change in flux. Remember that, please. So whenever we have a change in flux, we have induced EMF. Otherwise, we don't have any induced EMF. The initial flux is equal to 0 when it is out. But when we move it in perpendicularly, now the field and the plane are perpendicular. So the final flux becomes maximum. So the change in flux becomes positive maximum. So since I have a change in flux, I will have induced EMF, which will be maximum. But there is a negative here. We will learn why there's a negative here in Lenz's law. In all of them, the initial flux is 0 because in all of them it is out of the field. The final flux here becomes less than maximum. But do I still have a change? Yes, I do still have a change, but the change is less than maximum. So this will also be less than maximum. Here the final flux becomes 0. So as you see, initially it was 0, finally it is 0. So there is no change. The change is equal to 0. Since the change is equal to 0, there is no change, there is no induced EMF either. Remember this is moving a coil in and out of a magnetic field perpendicularly. In section 2, you will see similar perpendicular and parallel combinations again, but in section 2, it is for rotation. So first you have to decide if the question is asking about in and out or rotation. Since we have a change in flux in 3 different ways, this one is by having a rotation. So if I have a rotation, the last part C, that is by simply rotating a coil, a loop in a magnetic field. There are 2 types of rotation you have to pay attention to. Let's have a magnetic field that is to the right and a coil. As I rotate this coil like this is the rotation. So I'll be rotating the coil in this direction. Do I have a change in flux? No, there is no change in flux here. Although I have rotation, I don't have a change in flux. So since there is no change in flux, induced EMF is equal to 0. There is no induced EMF. So the rotation must cross the magnetic field. Let us have a coil that has a shape like this, and I will rotate these are magnetic fields. If I rotate the coil like that, as you see, now I will rotating it like this. The flux is 0, flux is maximum, 0, maximum. So can I say that I have a change in flux? Yes, we do have a change in flux in this case. So we have a change in flux. Okay, which is maximum. So induced EMF is also maximum. Of course, if you rotate it 90 degrees, it will be maximum. We have figured this out. Let's move on to this one. We will be trying to find the direction and magnitude of induced current. So we will be finding the magnitude. We can find the magnitude of the induced current but not directly, not right away. So we have to find the magnitude of the induced EMF first, and we will be using the Ohm's law, which is induced EMF divided by R. But how can I find induced EMF? By using Faraday's law. Faraday's law helps us to find the magnitude of the induced EMF. What about direction? If I want to find direction of the induced current, how can I find it? By finding the direction of the induced magnetic field too. That's also found by using Lenz's law. Let's talk about Lenz's law. Let us copy the magnets that we had a moment ago. I'll be copying this one more time. First, we'll talk about Lenz's law in a simple way, and then we will talk about the original Lenz's law. Lenz's law in a simple way will be like this. If a magnet moves toward a coil or a coil moves toward a magnet, they will repel each other. So if I have moving toward, they will repel each other. If I have moving away, then they will attract each other. To have repulsion, they need to have the same pole. So they will have like poles, because like poles repel each other and unlike poles attract each other. Let us apply this rule, and since this is moving toward the coil, this side will be also north, this side will be south. So use the right hand rule that you studied in section 2 of chapter 5. The thumb is always toward the north, and the four fingers will be the direction of the current. So automatically you will get this direction. Look at the right side and left side. At the right side it is moving up, at the left side is moving down. So the current will be from left to right inside this resistor. Here, when the north goes away, we will have unlike poles. So to have unlike poles, this side will be south, this side will be north. Reverse the curling right hand rule. You will see that the four fingers will point downward. So at the right side it moves down, at the left side it moves up. So the current in the resistor will be from right to left. Now that is Lenz's law in simple terms. So what is Lenz's law is originally talking about? It is saying that the direction of the induced magnetic field is in a way, this part is important. It doesn't oppose the external always. It opposes the change that created it. The change that created it. Now, let's go back. What kind of change do we have? The first one is increasing, which is the case of the moving toward. In the second one, it is decreasing. We only have these two changes. An example for the increasing, it was the moving toward. An example for the decreasing was moving away. So when it is increasing, it doesn't want the field to increase. When it is decreasing, it doesn't want the field to decrease. So what does it do? It will always oppose this change. Let's say that the field is increasing and the field is to the right. And this change is increasing actually. So it will try to weaken it. So it will try to weaken it because it doesn't want its field to increase. So it will be in opposite direction. This will be the induced one by being in opposite direction to the external one. But in the case of the it doesn't want it to decrease, so it will try to support it. The external one is decreasing, so it will try to support it. So it will be in the same direction. Another example for increasing and decreasing is when you close a switch. Another example for decreasing is when you open a switch. So that is Lenz's law. Let's talk about Faraday's law. Faraday is saying that the induced EMF is directly proportional with the rate of change of the flux. In physics, whenever we have a rate of change, it is always divided by delta time. So now the rate, delta time divided by the time of change of magnetic flux. The faster you change the flux, the more induced EMF you will get. And let's say that I have 10 turns and each turn produces 1 volt. So As number of turns increases, the induced EMF also increases. So I will have a total of 10 volts. And when we combine these two together, we get N change in flux divided by delta time. And if you remember, we said that Lenz is saying that the induced one is always opposing the change. So if this one is positive, this one is negative. If the change is negative, this one is positive. So how can we compensate for that one? By having a negative in front of the equation. Let's analyze this equation a bit more. The induced EMF is equal to minus N. That is change in flux. So delta, either A or B, multiplied by cosine theta delta time. Why did I take the cosine theta out? Because if the angle changed, the equation totally changed, which we will be talking about it in section 2. Now, the unit of induced EMF is volt. N doesn't have any unit. The unit of area is meter square and B is Tesla. So again, I have Tesla times meter square divided by second. You can say that it is also volt is equal to Weber divided by second. You can rearrange it and you can play with the units. So Weber will be equal to volt times second. Let's talk about self-induction. Let's have a coil. The symbol of a coil is simply a coil. Let's connect it to a DC source. In a DC source, the smaller one is always negative and the bigger one is always positive. Let's have a switch. And right now, there is no current. The current is equal to 0. So I have 4 cases in this one. The first one, when the switch is open. And I can see that the current that comes from the source is equal to 0. The magnetic field is equal to 0. And the flux is also equal to 0. The change in flux is also equal to 0. So there is no induced one right now because the change is 0. And the current is also, that's induced, is also equal to 0. As I close the switch, what happens? The current goes to maximum and the magnetic field also goes to maximum. So the flux also goes to maximum. Now, do I have a change in flux? Yes, I do have a change in flux. So the change in flux is increasing because it is going from 0 to maximum. So if you remember, we said that whenever we have a change in flux, we have an induced EMF. So I will have an induced EMF, but this is opposing that one. So it is in the opposite direction. So I will have induced current, which also will be maximum, but minus. This minus means that the induced current is opposite to the current that comes from the source. So it is opposite to I that comes from the source. So now I have two currents, one that's coming from the source, one that's induced due to the change in the flux. The change in flux was because the current was changed in the coil. In the third case, let's have the switch closed all the time. It is maximum, it stays maximum. It stays as maximum, maximum. There's no change because it is maximum, it stays as maximum. So since there's no change, there is no induced, so there's no induced current either. In the fourth case, the moment of opening the switch, it goes to 0 because I will be opening it. The field also goes to 0. The flux also goes to 0. Now, do I have a change? Yes, we do have a change. The change is decreasing because it is from maximum to 0. So it is minus maximum. I will have an induced EMF which is plus maximum. So the current will also be plus maximum. This plus indicates that it is in the same direction as I of the source. Let's go back to the beginning. Whenever we have a change in I of the source, we have a change in flux, which causes an induced EMF, an induced current. So we can clearly say that whenever we have a change in the current that comes from a source, we will have a change in magnetic flux. As a result, we will have induced EMF, which will also have induced current, induced field, and so on. Since there is no external source, it all happens because of itself. We will call this one as self-induction. Self-induction. This is called as self-induction because it all happens because of a change in a current that passes through the coil. There is a fifth way, which is talking about the rheostat. As we change the position of the rheostat, it is changing the resistance. The current also changes. As the current changes, there will be a change in flux. There will be an induced EMF, induced current, and so on. Faraday was saying that induced EMF is equal to minus N change in flux over delta time. So the faster I change the flux, the more EMF I get. Change in flux in this particular example depends on the change in the current. So if I change the current multiple times a second, I will get the same multiple times of change of flux. So the change in the flux depends on the change of the current. But their numbers are not equal because their units are not equal either. This is Weber per second, this is ampere per second. So what do? We will say that this minus n, we will multiply by a constant and delta I over delta time. So instead of delta flux over delta time, we will write a constant multiplied by delta I over delta time, and that is the induced EMF. Let's rearrange the equation. The equation will be minus, we will name this one as L, delta I over delta time. This L will be called as coefficient of self-induction. The unit is Henry. The unit is Henry. Let us talk about the units. So this one is volt, EMF. This one is Henry, which is ampere divided by second. Rearrange it. Henry will be equal to volt times second divided by ampere. What's volt over ampere? Volt over ampere is ohm times second. So Henry has multiple equivalent units, which you can find by using all of the equations that contains L. Are these two equations equal? Minus N change in flux divided by delta time, which is equal to minus L delta I over delta time. They are equal because we got the second equation from the first one. Can I cancel the minuses? Yes. Can I cancel delta times? Cancel them. If current is constant, the flux will also be constant. So cancel the deltas then. So what do we get? We get N flux will be equal to L times I. That is our second equation for self-induction. The previous one was the first equation. So this is our first equation for self-induction, and this is our second equation. Let us play with the equation a bit more. Flux is equal to A times B. Since it is on its own flux, it is always maximum, so we will not write the cosine here. And the magnetic field for a solenoid B is equal to mu n I over L. Let us write it instead of the equation. I have an N here, I have A here, and instead of B, I will be writing mu n I over L, which is equal to L times I. Now I can cancel the currents. I and I will cancel each other, and N becomes N squared. So I will have an equation that will be L is equal to the mu N squared times area divided by L. The most important point here is that if I increase any of these, this one will increase. But L is directly proportional with the magnetic permeability. So if you increase magnetic permeability by 10 times, L will increase by 10 times. L is also directly proportional with area. So if you increase area by 10 times, the L will also increase by 10 times. But if we increase the number of loops by 2 times, the coefficient of self-induction will increase by 4 times because we have a square here. And L is inversely proportional with the length. So as length increases, the coefficient of self-induction decreases. That is everything about coefficient of self-induction. The last topic in section 1 is eddy current. And eddy current is actually if you have a conductor that has a certain area, and if you change magnetic flux on this conductor, you will have a current, but the current is circular. Okay, so it needs to have a certain area first, and when you have an area, the electrons actually will follow a circular path. That's why you have a circular current. So the electrons will follow a circular path, and these are called as eddy current. This circular current is called as eddy current. As the electrons move in a circular path, they produce two different byproducts. Every current has a magnetic field and heat. Since these electrons are drifting in a very short area, they produce a huge amount of heat. So we have different applications for these byproducts. The first one, second one, and third one. So we have three applications for eddy current. The first one, it is used in making furnaces because of the heat. It produces a huge amount of heat. And we can also use it for a car braking system because of Lenz's law. If you increase it, it will try to repel it, so it will stop the wheel right away. The last one, it is used to detect metals in undergrounds, or it is used in airports. So this is the last topic in section 1.